in our group, we study basically three themes. We study, first of all, spin waves in magnetic materials, but then we also use NV center spins to detect the magnetic field of electronic currents in low-dimensional materials. And we are also working on developing the technique of NV center magnetometry. Now, this talk I will focus on spin waves. Just a small introduction. So spin waves are these collective excitations in magnetic materials. People are trying to use spin waves for information processing purposes, to make logic circuits using spin waves. And here you can see, for instance, a directional coupler built from magnetic materials. But then there are also many hot, more fundamental research topics. So this is one where people try to study spin wave physics at the single magnon scale. So you see a small magnetic ball here that has a, if you cool it down, it doesn't have any thermal spin waves, and you can make a single magnon go back and forth between the qubit and that ball. And then there's also a lot of interest in two-dimensional magnetic materials since their discovery in 2017 in their monolayer form. And about those materials, very little is yet known about their spin wave physics. So what kind of techniques do there exist to probe spin waves? There are quite a few, but I just list some examples here. Prominent examples. On the left, you see two optical techniques. One is Rouen light spectroscopy. It works by detecting the frequency shift of reflected light of a magnetic material. And you can study both the intensity and the phase of the spin waves by monitoring this light signal. Then we also have the Kerr effect. So that's a rotation of the polarization that you get when you let light interact with a magnetic material. It has very good time resolution, as you can see here. So this is kind of a spin wave propagating in time and in space on the x-axis. Very good time resolution, also optical technique. Then in spintronics, there is this technique called the spin Hall effect, where you can inject spin waves via a heavy metal electrode into a magnetic system. And this is a nice technique if you want to make devices, because well, you convert an electronic signal into a magnetic signal. Now, in this talk, I will introduce a rather new technique, and that is magnetic imaging of spin waves. And so it's the content of my talk. I will introduce the technique of NV center magnetometry, show how we use the technique to image coherent spin waves using this setup that I already showed. I'm looking through some metal electrodes here. And then we are also working on high resolution imaging of spin waves using a scanning NV diamond probe that you see here, where a 2-micron nano pillar with a nano scale diameter has a single NV at the very end, and you can use it for high resolution imaging. And in addition, I will show some nonlinear effects that we have detected using NV magnetometry. So the sensor is the nitrogen vacancy center in diamond. It's this nitrogen atom adjacent to a vacancy in the diamond carbon lattice. And it has a spin, an electronic spin that you can read out optically. So it photoluminesces when you shine with a green laser on a diamond. And when you do so, you see a picture like this. So this is the red photoluminescence that is emitted by a diamond under the excitation with a green laser. And if you tune the implantation density of these NV sensors correctly, you can address them individually. Now, this means that you have atomic-sized magnetic field sensors inside your diamond, and then that you can use for magnetic imaging. And then the major challenge is how to get these NV sensors close to the material of interest that you want to study, because in the end, that sets your spatial resolution of the technique. In my group, we developed two techniques. So the first one is very simple. We take a diamond with many NV sensors inside that are implanted very shallowly below the surface, 10 nanometers below the surface, and we just put it on top of a magnetic sample. So in this case, yttrium iron garnet. And then we can study using these NV sensors the magnetic fields generated by the spin waves in the YIG. A second technique is where we go to the nanoscale and we use a scanning nitrogen vacancy tip with a single NV at the end of it. Now, how does the technique work? So the NV center electron spin is it's a spin, and therefore its energy levels splittings depend on magnetic field. And this is what we use to determine basically the static magnetic fields. So these are the energy levels, and you can see that the splitting between those levels depends on the magnetic field. And therefore, if you can detect that splitting, you know the magnetic field at the site of the NV center. Now, how do you read out this splitting? You do so by applying microwaves to the NV center and monitoring the photoluminescence. And when the microwaves hit one of these transitions here, you will see a dip in the photoluminescence. Now, this dip tells you two things. First of all, the frequency at which the dip occurs tells you the static field at the site of the NV center. And secondly, the amplitude of the dip tells you something about the strength of the microwave magnetic field. And it's the latter that we will use to study spin waves in this talk. Now, how do we study spin waves? Let me start by the simplest technique, where we put a diamond on top of a YIG film, and then we send microwaves into this gold strip line here, and then we expect to excite spin waves downwards here. Now, how does it work if we just take a look at the spin wave dispersion? So what we're doing is we apply microwaves of a certain frequency omega, and therefore, because we know the dispersion of the spin waves, we expect a certain wavelength to be excited in this case. And what we do then is, using the NV centers, we monitor the amplitude of the electron spin resonance of the NV center, so the amplitude of the dip that I showed you previously. And what we get then is a spatial image of this amplitude, and it reveals, in this case, the wavefronts of the spin waves that are generated inductively by this microwave strip line here. Now, the spin wave is a traveling wave, but what you see in this picture is a standing wave, and that is because we apply a small trick. Namely, we let the spin wave microwave magnetic field interfere with a homogeneous microwave magnetic field. And that leads to a standing wave pattern in the stray field. So this is how we detect spin waves, how we can image them using NV centers. And again, to provide a little bit more insight in how this works spectrally. So I plotted here again the NV detection frequencies. So those are the ESR frequencies, these blue and red lines, and in the background you can see a sketch of the spin wave band, where the green line is the ferromagnetic resonance, and then above the ferromagnetic resonance you are exciting finite wavelength spin wave. So in this measurement down below, we are approximately at this star. So we apply a frequency that is resonant with the NV center, and we excite spin waves with that same drive frequency, and then the amplitude of the NV resonance tells you the spin wave amplitude. Now, we can use this technique to study spin waves in various systems. So for instance, we did some measurements on probing interference of spin waves and their chirality. So what you see here is a magnetic image. So again, a picture of the microwave magnetic field of spin waves in YIG, measured with a layer of NV centers on top. And we made two strip lines here. Here and here, you don't see them because they don't generate a strong enough magnetic field. But then the spin waves that are excited by these strip lines, you see very well. And there's two things that are remarkable here. So first of all, you see this far field interference pattern between these two spin waves sources. And then secondly, you see this very anisotropic shape, which is caused by the anisotropic spin wave dispersion. They're also very chiral. So these are waves excited in the Damon-Eschbach configuration that travel downwards from the strip line. We don't see anything above the strip line. On the right, I show a picture where we use NV centers to image the microwave magnetic fields of spin waves that travel below a metal electrode. So here on the right, you see an optical microscope image. It's a metal electrode, completely opaque to light. It's 200 nanometer thick. But the microwave magnetic fields actually penetrate very well through such metals. And we can look at the spin waves underneath such metal electrodes and therefore study the interaction with the metals. And that's what we did. So here we looked at this process in a little bit more detail, imaging the spin waves underneath a gold electrode as a function of the drive frequency, and trying to see what effect does the gold now have on the spin waves. And what we find is, if we take a line cut, is that the spin waves damp very fast underneath the gold, and they have very low damping, as we know in the bulk of the YIG. So YIG is a very low damping magnetic material. Now, this 100-fold increase in the damping underneath the gold electrodes can be explained by eddy currents. And if you you measure the damping as a function of the spin wave wavelength, then you see that underneath the electrodes you get much higher damping than next to the electrodes, which are the blue dots here. And by analyzing the amount of damping, you can actually extract the metal conductivity. So more generally, you can use these spin wave magnetic fields to study the magnetic susceptibility of stuff that you put on top of the magnet. So you can, for instance, study their permeability, you can study the skin depth or the conductivity. You can also put other magnetic materials on top and study the interaction with other magnetic materials. And you can potentially look at gated devices, because with top electrodes, and then look through at the spin waves through the electrodes. Now, let me switch to our experiments on nonlinear spin wave physics. So here our idea was that we want to use the NV center in diamond as a microwave detector. And this has a challenge, namely that the NV center can only detect microwaves at its ESR frequency, as I described earlier. It's very narrow band. It's about 100 kilohertz or a megahertz bandwidth that you have. And you can tune the ESR frequency using an external magnetic field, but sometimes this is undesired. And if you then want to detect a microwave signal that is not resonant with the NV, you can't do it. The NV center only detects microwaves resonant with the NV. Now here, our idea is to use a spin wave system to frequency convert microwaves to the NV frequency. It's sketched in this picture over here. So again, we have a strip line on a YIG sample, and our goal is to detect a spin wave that is not resonant with the NV center. In fact, it's far detuned by hundreds of megahertz or even a gigahertz. How do we do it? Well, what we can do is we can apply an auxiliary pump field that converts via spin wave mixing the frequency of the spin wave to the NV frequency. So how does this work? Well, this is one particular protocol that we developed. So we convert spin wave signals via so-called four-wave mixing. How does it work? We apply a pump field of a certain frequency, and then if there's a signal field present, we get a spin wave mixing, and there will be a mixing product that is resonant with the NV center frequency, like this. So in optics, this is called four-wave mixing, so that's why we call it four spin wave mixing as well. So again, an auxiliary pump field makes the detection of this signal field possible. So if we then try to detect a signal field using our NV center and monitoring its PL, its photoluminescence, then rather than just seeing a dip at the ESR frequency of the NV center, we can now see dips at over a very wide bandwidth. This is because the pump converts the signal frequency to the NV frequency. So you see this pump arrow is always halfway between our signal and our detection frequency here. The detection frequency is set by the NV center ESR frequency. So if we apply a pump of this frequency, we are sensitive to a signal at this frequency. If we apply a pump at that frequency, we are sensitive to a signal at that frequency. Now, we can also use this to drive coherent NV spin rotations with a very much detuned microwave field, because this conversion process is very coherent. So here we measure Rabi oscillations of the NV center spin using a very much detuned fields, and it allows, say, full control over the NV spin via detuned microwave fields. That's kind of the new thing here. So the message here is that this conversion enables sensing over a gigahertz bandwidth, and it also provides some insight into this nonlinear spin wave physics, this four-wave mixing process. Now, if we increase the drive power, we can even see a whole coombe of spin wave frequencies, so which we can detect with the NV center. So this kind of yields sensitivity to multiple frequencies at once. So here we can see, as a function of bump frequency and signal frequency, the response of the NV center photoluminescence, and it's basically explained by the formation of a frequency coombe. Now, if we want to image nanoscale spin waves, we have to go to a higher resolution technique. So that's why we use this sensor spin embedded in a diamond scanning tip. Now, this allows us to image spin waves that are approximately 300 or 400 nanometer in wavelength. At the moment, we are limited to spin waves that are still resonant with the NV center ESR frequency. That's why we can't go lower. But in principle, this technique has the sensitivity to detect waves on the 50 nanometer scale. Now, in addition, the advantage of this technique is that you can actually touch down with the tip onto a magnet and thereby put your NV center very close to the magnetic material. And that makes it very sensitive, because now we can detect also thermal spin waves. And we use this to study magnon gases that are produced by the excitation of coherent spin waves. It's based on a former idea where if you drive the ferromagnetic resonance here of a magnet, you basically get an increased magnon band occupation. And we have shown with our scanning probe that this also is the case when you apply or when you excite a directional spin wave that only travels to the right, and that wave leaves in its wake an incoherent magnon gas, so a high occupation of magnons at a totally different frequency than the frequency of the wave itself. Now, let me end with an outlook. So we want to go to thinner magnets. There are many unknowns in these van der Waals magnets. What is their magnetization, spin wave spectrum, etc. I would like to thank the people that did the work. Jacopo just finished his PhD. Brecht and Samer did the scanning probe measurements, and all the other people in the lab helped in some way or another. And with that, I would like to leave you with my summary slide. And thank you for the attention.
Thank you, Professor Vanessa. So any question from the audience? So Professor Demokritov, please.
Okay, can you hear me?
Yes.
Yes. My question is, you said in the beginning that there are different techniques to map and detect spin waves, and one of them was brilliant light scattering. And I would like to hear from you in what sense there is an advantage of this technique with respect to spin waves, because what you have shown up to now can be easily detected by brilliant light scattering, except probably a spatial resolution of 15 nanometer, which is really advanced. What is the advantages of this technique with respect to Bellis?
Yeah, thank you for the question. So there are basically two ways of approaching this question. So first of all, I'm also interested in using magnetic fields to manipulate NV centers themselves. And spin waves make rotating magnetic fields that are very effective in driving spins. So you can use the spin waves to manipulate NV centers. And I think that for me is a major motivator. Secondly, the techniques are different. So NV centers detect magnetic fields rather than light that is scattered by a magnet. So if you want to understand the magnetic fields generated by a spin wave, then this is a good technique. Also, like I showed, these magnetic fields, they penetrate through metals, so you can, study spin waves through metals if you want. But for the rest, so a weak point of the technique is its time resolution. There's little time resolution because you need some time, for instance, you have time resolution, but you need to flip the NV spin. And that can happen only on the 10 nanosecond scale or so. So compared to pump probe optical experiments, this is very low.
And I would say that very narrow band, although you are proud about 1 gigahertz, but if you compare it with Brinell scattering, where you can go from half gigahertz up to 300 gigahertz, it's of course very narrow band.
That's also right. Yeah. So on the other hand, the spectral resolution is very good, right? So you can have the NV center only detects, say, in a 100 megahertz frequency, line, and that line you can then tune with an external magnetic field, in principle, all the way up to hundreds of gigahertz. But then you need to apply several Teslas of field. So there's always this question, you know, if you apply a field, how does the system that you want to study respond to the field? As well.
Excuse me if I ask a stupid question, but I have heard that this sensor, nitrogen vacancy, cannot work at high magnetic field. There is some limitation up to 0.1, 0.2 Tesla, and everything else.
I think I know what you refer to. So with the NV center, it's important that you apply the magnetic field, so the static magnetic field, along its axis. So there have been measurements at 10 Tesla already with 200 gigahertz ESR frequency. It's just a spin, you know, in the end. There's nothing strange there. But if you apply a field perpendicular to its axis, the spin-dependent photoluminescence quenches. So then you cannot use it. Yeah.
Okay. Thank you very much. Thank you.
Yeah.
Thank you.
Okay, so Professor Schumack.
Yeah, thank you for a very nice talk, very interesting technique. And my question, okay, there was some technical, but I think they answered. Let us switch to quantum magnonics. So if we are thinking about quantum magnonics, so we want to do job at millikelvin range, when we can excite single magnon, detect single magnon. And one of the largest challenges nowadays is actually source and detector. Do you think your NV cell could be potentially a good source of detector? So is it possible to make such experiment that you have a magnetic film, you have NV cell here, and then located a certain distance here, you switch one, it creates a single magnon, and second one will be switched. Would it be then, is it possible, first question, and would it be then a proof of single magnon excitation and detection?
Yeah, that is, of course, a very nice experiment that you propose. I think it's also very challenging. So indeed, you have to cool down the system so there are no thermal magnons. And then the question becomes, is the NV center, say, sensitive enough to detect a single magnon? And that very much depends on the exact geometry of the system that you're considering. For instance, if you have a confined paramagnetic resonance that creates a rather strong stray field, and you can put your NV center very close to that. So that is kind of the optimal situation that I can envision. And NV centers have been used to detect the magnetic field of single electron spins, also even of single nuclear spins. So also in specialized situations, I think it very much depends on how you exactly design your system and whether you are able to reach the right parameter regime there. But I think in terms of sensitivity, I mean, we are encouraged by the fact that we can detect the field of a single electron spin. Yeah.
Okay, thank you.
So any other questions from the audience? Dr. Wang, please.
Okay, thank you for the nice talk. I just follow the Professor Democritus the question. I think you also answered partially. You said the external field direction is also important because nowadays the brain light scattering, maybe there is some challenge for measure the outer plane magnetization for some small angle. So it's possible to also measure outer plane forward volume using your method. So we apply an external field outer plane.
Yeah, that's indeed an interesting question. So what you would need, or what would be optimal in that situation, is if your NV centers are also out of plane, compared to the diamond. And that is possible nowadays. So people can grow diamond with preferential NV centers that are out of plane. And then you can apply a field of, if you want, 10 Tesla along the NV axis. And these are challenging experiments because the frequencies will become very high, right? You go into the hundreds of gigahertz regime at 10 Tesla. But maybe if you go to 1 Tesla, things are easier and you can study spin waves in the frequency range of 20 to 30 gigahertz.
Okay, but if I want below 10 gigahertz, is possible? Or?
In principle, it is, but the question is, can you make your magnet? Yeah, no, it is. Yeah. Well, so the details depend a little. It depends a bit on the details, I have to say, because the NV center ESR frequencies depend on the magnetic field that you apply. The spin wave spectrum also depends on the magnetic field you apply. Right. So if you want to use this resonant technique, you have to find a regime where it is allowed. Now, maybe via these kind of mixing effects that I also described, so you apply 2 frequencies and you make use of the nonlinearities to convert frequencies, then you can do things over a broader range. Yeah.
Okay, thank you very much.
Yeah, thank you.
So any other questions from the audience? Okay, so if not, let's thank Professor Vladislav again.
Thank you.
And yeah, let's move to the next speaker. So next speaker is Dr. Paul Keatley. So Dr. Keatley, are you there? Yes, thank you. Wait, I can see your slide. So could you go to the presentation mode, maybe?
Okay. Can you hear me?
So yes, I can hear you. Yeah.
Excellent.
Yeah, okay. So our next speaker is Dr. Paul Keatley from the University of Exeter. So the title of the talk is Optically Detected Spin Orbit Torque Ferromagnetic Resonance in an In-Plane Magnetized Ellipse. So Dr. Keatley, now we see not the presentation mode, is we see your practice mode. So we see a small screen.
Okay, one moment. How is that?
Yes, now it's okay. Thank you.
Excellent.
Thank you. So,
perfect.
yeah, please start. Thank you.
Okay, so thank you for the introduction and the opportunity to present our work at the ICMM2022. Title's already been mentioned. So this work's a collaboration between the group of Rob Pickin at the University of Exeter and the group of Jordan Katine at the Western Digital Research Centre in San Jose. And more details about this work can now be found in the publication in Applied Physics Letters. So why should we use a local phase resolve probe of spin orbit torque ferromagnetic resonance in an in-plane magnetized device? So microscale nanoscale elements support localized modes, and that's due to the in-plane demagnetizing field, and which gives a non-uniform internal field. And these Brillouin light scattering maps show that you can have localized modes that have a spatial character that depends on the applied field. And so ultimately that can lead to a non-uniform dynamic response to spin orbit torque. And electrical measurements tend to probe the net orientation of magnetization. So if you want more information, you need to use a local probe. But also, furthermore, localized modes will allow us to probe spin orbit torques in specific regions of a device too, because of their localized nature. And time resolved scanning curve microscopy, which was mentioned by the previous speaker, that complements electrical measurements by directly probing localized modes to characterize non-uniform spin orbit torques in microscale devices. So this is how our devices look. They're platinum based. It's a 6 nanometer layer of platinum with a cobalt iron boron ferromagnet on top, which is 2 nanometers thick. And we make electrical connections using microwave probes, as shown in this photograph. And the schematic here shows that we're passing, if I go to laser, okay, we're passing our currents through the signal line through to the ground through the wider electrical contact. And at the center of this Hall cross of platinum, we have this microscale ellipse, which is 800 by 2000 nanometers in size. And it has an easy axis, which is perpendicular to the current direction. So we're only using the current lead for these measurements. We're not making any electrical measurements. And the spin Hall effect in the platinum generates a spin polarization at the platinum ferromagnet interface. And these particular devices are very good for optical measurements because they got good optical access with no top contact. So the measurements are performed in this way. So we mount our sample on a piezoelectric scanning stage. We apply a biased magnetic field with an angle defined here with respect to the easy axis. And as the current passes through, we have an associated Ørsted field, which is perpendicular to the current direction and in plane, and also the spin polarization in the same direction. So then we use a microwave synthesizer to generate a modulated 3.2 gigahertz microwave waveform and a bias T to also apply DC current. And that allows us to investigate changes in the spectral line width due to the spin orbit torque. And then to probe the dynamics, we synchronize the synthesizer with a femtosecond laser. We use second harmonic generation to go to blue light so that we can focus to a smaller spot. And that light is time delayed and then linearly polarized and then focused to a diffraction limited spot, which is submicron. And then we measure polarization changes due to the magneto-optical Kerr effect using a balanced photodiode detector. So the spatial resolution is estimated to be about 300 nanometers, temporal resolution down to picoseconds, and we're using less than 200 microwatts average power to prevent any sort of heating due to the laser. And by measuring the full reflected beam, we can sense the outer plane component in the magnetization by the polar Kerr effect. And if we block half the beam, the high numerical aperture lens allows us to access the longitudinal Kerr effect. And the types of measurements we perform, one is to fix the position on the sample and scan the time delay, so that's a time resolve scan. Or the other two measurements are to fix the time delay and scan the position for time resolved image, or sweep the field, which gives us our spin orbit torque FMR spectrum. So some preliminary static measurements then. So these are just reflectivity images showing the device. This is the wider current lead and the slightly higher reflectivity at the center. The cross is the ellipse, and that's a zoomed in image with the ellipse defined schematically there. And using the longitudinal Kerr effect, we can demonstrate that this indeed has uniaxial anisotropy by blocking half the beam. And then preliminary measurements to find the resonance conditions then. So the first thing we do is we use a picosecond sort of broadband pulse excitation rather than microwaves, and to look at the precession signal for a particular bias field. So here we use 200 Ørsted, for example. Then we can extract the frequency from Fourier transform and then apply a single frequency microwave excitation at that frequency. If we image at opposite antinodes of this signal, say here and here, for example, we can see that we have dynamics which have larger amplitude at the center of the ellipse. So this is most likely the center localized mode in this ellipse. And so that means that hopefully we'll not be too sensitive to any edge effects in this particular measurement. And then rather than imaging, if we sweep the magnetic field, if we set the phase to either a node or an antinode instead, and sweep the magnetic field, we can get sort of real and imaginary type ferromagnetic resonance curves for this device. And so this is our locally probed phase resolved spin orbit torque FMR measurement. Let's have a look at the angular dependence on the in-plane field applied to the device for a DC current of 10 milliamps. So this is the largest current we use in these measurements. So this is starting from a high current situation. So for the field applied along the easy axis, we don't see any signal at all. And that's because the Ørsted field associated with the current and the spin polarization are both parallel to the magnetization, so there's no torque. If we go to the hard axis, then we see some nice resonance peaks, and they're actually quite similar in sort of line width and amplitude. And this is the high torque condition because the spin polarization and Ørsted field are now perpendicular to the magnetization. And then what's interesting is as you go slightly away from the hard axis, maybe 30 degrees, there's a marked broadening and narrowing of the FMR line widths and an associated reduction and enhancement of the amplitude of the resonance. And if you go to the other side of the hard axis, you see that these changes swap over. So for example, on the positive field side of of remnants. For one side of the hard axis, it narrows, and for the other side, it broadens. We can change the phase of the microwaves by pi/2, and then measure the other component of the ferromagnetic resonance, the other component of the magnetic susceptibility. And all these curves can be well reproduced by macrospin calculations. And here we're not assuming any quasi-alignment because the bias field is quite small. And from these calculations, we extract damping parameter of about 0.025 and a spin torque parameter of 6.75 times 10 to the minus 7 amps per centimeter squared. So here's the angular dependence for 10 milliamps case then. So there's a twofold sine squared 2 theta term due to the uniaxial anisotropy, and then a one-fold cos squared theta due to the DC Ørsted field. And this was the interesting feature. This was the line width, and we have changes as you go across the hard axis at 90 degrees. You have changes from a broad line width to a narrow line width, and then for the other side of remnants, you go from a narrow to a broad resonance. And you can use that to try and estimate the damping parameter and the spin torque parameter. So we interpret these changes as due to the direction of the magnetization. So if the magnetization is canted to one side of the hard axis, you have a component of the magnetization that's parallel to the spin polarization. And if it's canted to the other side of the hard axis, that component is anti-parallel. So through the in-plane torque term, we think we get these changes in the line width and the amplitude of the resonance. So to extract the damping parameter and spin torque parameter, we use the macrospin calculations to first reproduce the damping parameter. So we just ran calculations for a range of alpha and then looked to see when it matched the line width of the measurements. The blue line shows the average line width, and the gray band is the uncertainty. And we find a damping parameter of about 0.03. We can then do a similar thing. We use the damping parameter of 0.03 and then vary the spin torque parameter to see when the line widths of broad and narrow peaks slightly away from the hard axis match. And what we found is this: for the solid symbols here, we see there's a significant discrepancy. We see for the broader line widths, the spin torque parameter is down here somewhere, and then for the narrower line widths, it actually doesn't cross at all. But if we reduce the damping parameter from 0.03 to 0.025, that shifts these curves down, and so then there's better consistency with the matching of the line widths for the broad and narrow cases. And so then that allows us to infer that the damping parameter is actually around about 0.025, and the spin torque parameter is this value 6.75. And we think this slightly reduced value of alpha is due to other damping mechanisms such as 2-magnon scattering, which are not included in our macrospin calculations. If we go to a lower current condition, so 1 milliamps, we actually don't see, away from the hard axis, we don't see this marked broadening and narrowing at all. So if we try and do the similar analysis, we actually see a larger value of alpha, which may suggest that there's actually no thermal effects going on here, because you may expect a larger damping parameter when the DC current is higher, which we didn't. If you try to vary the spin torque parameter in the calculations and compare them to the experiment, we actually find that the variation in spin torque parameter from the calculations is less than the uncertainty in the experiment. So we can't infer anything from those calculations and measurements. But a measurement of the line width as a function of DC current on the hard axis confirms that there's no sort of discernible broadening of the resonance peaks as you increase the DC current. It remains in the uncertainty. So that suggests there's no thermal effects. And so in summary, we've used time-resolved scanning curve microscopy to perform locally probed phase-resolved spin-orbit torque ferromagnetic resonance measurements. We use the center localized mode to probe the spin-orbit torques at the center of the ellipse. And we need to incorporate both the Ørsted field and the spin-orbit torque to reproduce the asymmetry of the measured peaks. We can then use that to determine estimates of alpha and ST parameter using the calculations, and we've ruled out thermal effects. So the use of time resolved scanning curve microscopy as a direct probe of localized modes in microscale devices goes beyond the spatially average capability of popular electrical measurements and paves the way towards spatially resolved measurements of spin orbit torques. So with that, I thank you for your attention and welcome any questions.
Thank you, Dr. Keatley. So Professor Demokritov, please.
Okay. Hi, Paul. Thanks for a nice talk. I have a technical question. You said that you have possibility to work with the full beam and with the half beam, and you define the resolution. I wonder, is it the resolution 300 nanometer for the full beam? And what happens with this resolution if you make half beam? Is it the beam becomes broader, you lose the resolution, or it's approximately the same? Thanks.
Yeah, hi Sergey, thanks for the question. Yeah, maybe you get, so the beam is actually blocked as it goes back to the detector. So the spot on the sample is actually the same as in the polar case. It's just that you reject half of the beam so that any polarization rotation in the beam is, it still has a polar Kerr component, but if you're making an in-plane hysteresis loop measurement, you don't expect an out-of-plane component for a static measurement. So to answer simply, yes, the spot size is the same, and then you get.
So you are not working with one half beam. One half beam is incident, and the opposite half beam is detected. You just illuminate with the full beam and just detect only one half of beam.
Yes, that's right. Yeah.
This is the technique. Okay.
Yeah.
Thanks. Then it's, of course, the resolution is not suffering. Okay. Thanks.
That's correct. Yeah.
Thank you. So any other questions from the audience? Okay, so if not, let's thank Dr. Keatley again. And
thank you very much.
Thank you. And so we move to the next speaker, Dr. Gubanov. So Dr. Gubanov, are you with us?
Yes.
Thank you.
Hello, dear colleagues. My name is Vladislav Gubanov. I'm PhD student from Saratov State University. And I will be glad to present you a report, speed wave propagation magnetic waveguide with local laser heated region. The study of the possibility to create new types of information signal processing device of magnetic principles create great interest. Microstructures based on yttrium iron garnet films can be used in spin wave signals processing due to low damping to control the properties of propagate spin wave. Methods of structuring via IgG films to create irregular micro and nanoscale waveguides, including structures with broken translational symmetry, can be used. In this work, the research will be carried out using experimental techniques, the microwave spectroscopy and brilliant light spectroscopy method. Micromagnetic modeling produced by Lumax software. And in this work, to create heat region in experimental setup, we use laser radiation generated by source with a wavelength of 830 nanometers. And as you can see on the slide, we achieve a temperature between room and maximum of heating is 15 degrees. And in this work, we consider two types of structures. Structures with broken translational symmetry, like U-shape, and waveguide planar structure, to which we apply laser heating let us proceed to the first structure. It's a horseshoe-shaped structure, and heat was carried out in the area of rounding. One of the important things is as the wave passed in the waveguide, the type of waves is changed, and we and the parameter of the curvilinear coordinate was introduced in the structure, and on the left side of the slide we plot the distribution of the internal magnetic field. In the case if we applied an external magnetic field for the effective excitation of magnetostatic surface spin wave and backward volume magnetostatic spin wave, it can be seen that the distribution of the internal magnetic field is inhomogeneous. In the right side of the slide, we show the amplitude frequency response in case excitation surface magnetostatic spin wave and we compassion the amplitude frequency response at the input antenna and output antenna marked as P1 and P2. It can be seen that certain frequencies, the passage in output antenna P2 is downgraded. And if we applied laser heating in a rounded area, spin wave propagation is transformed, and in this slide demonstrate the amplitude frequency response for the case excitation backward volume and surface magnetostatic spin waves. If we applied local laser heating at the structure in the structure and without laser heating, it can be seen that the application of laser heating in case of backward volume magnetostatic, in the case of excitation of backward volume magnetostatic spin wave in a larger frequency range improves the passage of spin wave. In the right part of slide demonstrate distribution maps of the spin wave intensity obtained by beryllium light spectroscopy method at the excitation frequencies of 5.38 gigahertz with the applied of laser radiation. We control propagation of spin waves in case of backward volume magnetostatic spin waves. We turn off spin wave propagation. In case of surface magnetostatic spin waves, we amplify the spin wave intensity. In the next stage, we study the propagation of spin wave in the planar YIG film when the laser radiation is applied to structure. Also, in the experiment by BLS method, the phase resolution of the spin waves was obtained for this. For the purpose, an optical modulator was installed in the system, operated in the frequencies range 6.8 to 7 GHz. The phase resolution of spin waves using the BLS method was still shown in the works, and how laser heating and need shown how laser heating in order to obtain phase information of spin wave in the system, we have two pulses. First pulses for excitation of spin waves, and the second pulse for phase of modulator. These pulses have duration of 400 nanoseconds, and data about phase is calculated further using this equation. In the slide shown the phase and intensity of spin wave in case without laser heating applied structure, and this laser heating, it has been seen that the maps of spin intensity don't show change in mode composition. In case of phase distribution, the phase change when heating is applied. We show how transformed this slide shows the amplitude frequency response for the structure without laser heating and with laser heating. It can be seen in the green in the frequency 6.8 kHz. The transmission is dropped when the laser radiation is applied. To explain this, the distribution of the MZ component of magnetization component was plotted. It can be seen that during laser heating we have a heating point and envelope in the area of output antenna create condition for propagation of third width mode, and then we integrate the signal at the output antenna, we get power decrease. In order to explain the phase change, a magnetic simulation was performed in which the magnitude of heating was changed, leading to change the saturation ionization of the YIG film. And we have propagation wave with positive wave number and negative wave number. It can be seen that reflected was arises from the heating area, which has increased the amplitude with the given parameters when the heating changes. And as conclusion, thus, in the case of irregular structure with the application of local laser heating, there is a possibility to control the signal propagation turn on, turn off modes. With the application of laser heating, in case of planar structure, we can create condition for the rising of multimode regime. in area of the output antenna can achieve spin wave transmission switching off due to the effect of signal integration. Thank you for the attention.
Thank you. Thank you so much for your nice talk. So any questions from the audience? So Dr. Sheng, Lu Sheng, please.
Okay, thanks for the nice presentation. I just want to ask, for your device, comparing with our conventional microwave excitation, what's the advantage or the uniqueness? Thank you.
Thank you for the question. One question about how first device or second device. In first device, advantage for this structure, if we applied the laser heating, we the structure we applied external magnetic field in different orientation. We applied we excite the two types of spin waves, and if we applied laser heating, we turn on, turn off of spin propagation, and most advantages what we didn't we use advantages of irregular structure. Sorry.
Okay. Thank you.
Thank you.
Thank you. So any other questions?